Hello and welcome back to part 2 of the video on work. If you haven't watched the video of part 1, please go ahead and do that and then come back to this video. All right, let's get started. In example 1, we have a dynamic mixed with work problem. It says, according to the figure below, a horizontal force of 25 newtons moves on an object of blah, blah, blah. Now, of course, we don't have any figure yet, so we have to draw that ourselves, although it says according to the figure below. So let me draw that for you guys. Here we have a box. Let's imagine an object, right? That is quite rectangular, in fact. Now, this rectangular object has about 5 kilograms of mass. It's being pulled with a force of 25 newtons, and the frictional force is about 10 newtons. All right, so far so good. Now, if you want, you can pause the video at this moment and try to solve this on your own. If not, let's go ahead. All right. Now, first of all, I'm going to go ahead and draw the free body diagram for this, which I already have done, but I'm going to calculate the other forces that I think that are present. First things first, I got the weight, which is mass times gravity, and that's going to be about 50 newtons. Then I have the normal force, which is the force that the surface exerts to make sure that it's not breaking. That is going to be equal to the weight in this scenario. So that's about 50 newtons. I'm supposed to calculate the work done on friction and weight. I'm going to start with weight. Now, the work done on weight can be calculated by multiplying the force in the horizontal component and the change in displacement. As you can see, the work done on the weight regarding its force has a bit of a weird situation because the force is being applied in a perpendicular direction compared to the movement, because the box is going to move to the right, and it's actually they have a 90 degree angle between each other, and as a result the cosinus of 90, as you know, is equal to 0. But we also know that any time a force is applied at a perpendicular angle to the direction of movement, the work done on it is 0. So the work done on the weight is simply 0. And the reason is obviously because the force is being applied at a 90 degree angle. Now, in the second part of this problem, we're supposed to calculate the work done on friction, and we have to be careful about the angle that we're going to have to use. First of all, the angle of the horizontal force of 25 newtons, if we use the formula for work, F cosinus of theta times the change in displacement, the angle of the 25 Newton force is going to be 0, and that's because it's being applied in the correct direction, and so the angle here would be 0. The theta here is 0. But the 10 Newton force is actually 180 degrees away from that. And you can think about it, it's kind of in an opposing direction to the 25 newtons. So the theta between the 10 newtons and the 25 newtons would be about 180. All right, let's go ahead and calculate the work done on friction now. It's going to be the 10 newtons multiplied by the cosinus of 180 times by the change in displacement, which according to the question was 2 meters, an object about 2 meters. So multiply that by 2. The work done on friction is simply 10. Cosinus of 180 is -1, and that's going to be multiplied by 2. So the work done on friction is simply -20 joules. All right, let's go ahead and take a look at another problem now. All right, example number 2. According to the figure below, a truck is pulling or just towing a car with a constant force of 2,000 newtons. Calculate the work done by the truck. Calculate the work done by the truck in 2 kilometers. So basically the work done in 2 kilometers by that truck. Now, let's imagine that the car is right here. So this is the car, and it's being pulled by a truck. And let's imagine the rope that is attached to the truck. So this is the truck. It's all right, it's much bigger compared to the car. Here we go. Hopefully I can draw it out in a better shape than the car. All right, that doesn't look much like a truck, more like an elephant. Let's try to make that a bit more interesting. Nope, that did not work very well. All right, that looks a bit better. Let's bring that down now. And we can assume that this is the truck, of course, one that is not currently in production. All right, let's go ahead, and we've got the rear wheels right here. Okay, raise that up, and that looks a bit better. Got the window right here, and the door is currently on the other side, I guess. All right, so we got the car right here, and it's being pulled by the truck. Now, the force that is being applied by the truck is through this rope right here, and it's being applied at a 30-degree angle. So the angle between the rope and the car is about 30 degrees. Okay, now a bit of a vector component disposition right here. We've got one component in the y direction, and that would be f sinus of 30 degrees, and one in the x direction, and that's f cosinus of 30 degrees. We're going to be concerned with this f cosine of 30, which is the adjacent one to that angle, because the horizontal force is the one that's actually causing that, the towing. So in order to calculate the work, we just have to multiply f cosinus of theta by the change in displacement. Now, the force that's being applied by the truck is 2,000 newtons. That we already know from the question. The angle is 30 degrees, so 2,000 times the cosinus of 30. And the change in displacement is 2 kilometers, so that's about 2,000 meters. All right, let's go ahead and calculate this up. So cosinus of 30 is just radical 3 over 2, so 2,000 times radical 3 over 2 times 2,000. What happens next is that, so you can cancel out the 2 with that, get 1,000. You're going to get about 1, 2, 3, 1, 2, 3. So about 100,000 times 100,000, yep, 1,000, wait, yeah, 1 million actually times radical 3. Now, you can actually change that up to, I'm sorry, that becomes 2 million, because here this 2 and this 2,000 cancels out to give you 1,000, and then 1,000 times 2,000, that's about 2 million. So the 2 million, you can actually change it up to another bigger unit, so you can write this as 2 radical 3 megajoules, and that would be your final answer, because mega is 10 to the power of 6, which is a million.